So we're going to finish section 3.2. We're looking at addition of whole numbers and taking a look at other bases, which is where we left off last time as our last pieces. And I believe we're on mental math. Does that sound right?
Yes.
Excellent. So I mentioned last time that there are often confusion between mental math and estimation because there are some similarities between them, but mental math means that it's something you can do in your head. Estimation means you're approximating. So be careful as you're taking a look at specific questions, whether they're homework questions or test questions or whatever, that you're making sure to do the right thing that it's asking. So we're starting with mental math. Mental math is this kind of funny beast because, and those of you who've had prop and stat know we talked about it there as well, is that it needs to be something you can do in your head, but you're going to write down some of it on paper so that I can see what you're thinking in your head. So even though you're writing it down, it needs to be something that can be done without writing it down. You're just showing me it. So this is, there's going to be several strategies that we're going to take a look at with mental math, and we're just going to go through them kind of like we went with our other strategies last time. So the first one is adding from left to right. So the way that this strategy works is that we take the first number, doesn't even necessarily have to be the first number, and we break it apart, and it's similar to one of the strategies that we actually saw last time, into like the 46 into 40 and 6. And what we're going to do is we're going to add that, and then the 38 is 30 plus 8. So we're going to add the 40 and the 30 together, right? The tens placed together. And when we do that, we get 70. And then we're going to add the ones digits together, in this case 6 and 8. And we're going to get 14. And then we're going to add those two together, and we get 84. And that's 3 steps. So we're considering that to be sufficient, like small enough numbers of steps to be able to still maintain in our head at the same time. Okay, 3 steps. Added the tens digit, added the ones digit, and then we added those 2 resulting values together. Breaking up and bridging is a very interesting one. On this one, we don't break both numbers apart, so we kind of broke apart both the numbers here, right? The tens digits and the ones digits. Here we just break the second one apart, or it could be the first one, it doesn't really matter, but one of the numbers stays as is, so we'll just use the 46. And so instead of adding 40 and 30 together, we're going to add the 46 with the 30. Okay, so 46 plus 30 would be 76. And then we add the remaining 8 that we sort of ignored when we added the 30. And 76 plus 8, which is not exactly single digit addition like it was before, ends up giving us 84. But again, because we're only adding a 1-digit number, we consider that to be able to be done mental math in our head. So that's breaking up and bridging. We saw this one before. It was called opposite change before. So that is certainly another valuable name for it. They're calling it trading off here, but it works the same way. We have the 46 and the 38 that we're trying to add together, and we really do not want to add 2-digit numbers. So the goal is to change one of these and get it to be a 0 in the ones place. For example, on this one, it's really nice to add 2 to the second number, but I have to invoke the opposite change to the other number, or I have to do a trading off, right? I give 2 and I take 2 away. I add 2 and I subtract 2. So that's the trading off perspective here. So this one becomes 40 and this one becomes 44, which has addition without any regrouping. So the idea behind trading off or opposite change is to be able to do addition where there's no regrouping. No need to borrow, no need to carry, depending on whether we're adding or subtracting. We'll see a similar strategy to this when we get to subtraction. We talked about a strategy last time called making 10. Do you remember that one? Where we're thinking about numbers that add nicely to be tens. This next strategy is very similar. It's called compatible numbers. So instead of looking for necessarily things that add together to be 10, we're looking for things that add together to be something nice, which is still often 10 or 100, something like that. So we're looking for what they call compatible numbers. For example, the 40 and the 60 Those are very nice numbers to add together because they give you 100, right? There's another pair here that does that. Which is which? The 30 and the 70, which gives us another 100. Of course, I haven't done anything with the 50. So the 100 here, the 100 here, and the 50 here combine to give me 250. So again, we're finding exact values in all the ones we've done, yes? We've not approximated anything. We've just used some sort of a regrouping or breaking things apart so that the addition is easier. So these are great when the numbers really are compatible, but sometimes numbers aren't compatible, but they almost are. So 35 and 68 are almost compatible numbers. So the idea is to take one or the other of them, or it could even be both, but I think that usually sticking with one or the other is sufficient, and changing it just a little bit to make it a compatible number. For instance, what number can we add to 35 and get that nice whole number 100? Do you know what it is? 65. So we don't have 65, but we have 68, right, Hannah? Yeah. So what we do is we take the 68 and we break it apart into the part that would make it compatible and the leftover part. So these two numbers now are compatible numbers, right? Because they add to that nice 100, or if it, I mean, it could have been 1,000 or something too. It doesn't have to just be 100, but and then we have that extra 3, right? So this would be 103. So hopefully, even as you look at this, you're like saying, well, I'm not showing a lot of work. You're not, but it's enough that I can know what you're doing, right? I can see what you've done. If you've broken something apart, if you've added a piece and subtracted a piece, that's enough for me to see how you're thinking about the particular problem. And there's nothing you've done on here that so far that you haven't been able to do in your head. Now, maybe you don't like mental math, that's fine. But the pieces that we've done so far are pretty straightforward addition. There's not a lot of complication to them, and that's our goal, is to make the addition easier. Okay, so now we're going to actually switch gears and do the estimation part. So estimation, or this, your book calls it computational estimation. There are several strategies we're going to look at. They are not all used in all cases, right? Just like with some of our other ones, you know, there are some things that are nicer to use in certain circumstances. The first one's called Frontend Estimation with Adjustment. So let me actually talk about the front-end estimation because that's something that's separate from the with adjustment. This is like a two-step thing. Okay, so what I'm about to show you has nothing to do with mental math anymore, all right? It may be easier with the changes that we make to do it with mental math, but the goal is not to try to make it something you can do in your head, all right? It's just an estimation. Sometimes estimation is good enough, right? Do I have enough money to pay for the basket of groceries? I'm just computing as I go along. Yes, I do at the end, right? It's sufficient. So what we're going to do is, with front-end estimation, is we use just the first digit, okay? Hundreds digit in this case. So I have 300, 400, and 200. So 300 plus 400 plus 200 is what? 900, thank you, 900. And then what we're going to do is we're going to take a look at what's sort of left over, and that's these pieces, right? The 32, the 62, and the 25. And the adjustment part comes from those three pieces. We're looking at those three pieces to see if there's anything that's a compatible number or a nearly compatible number. So of those three, which two are nearly compatible? Yeah, the 62 and the 32, right? 60 and 40 are compatible, 35 and 65 are compatible. These are almost compatible numbers. Now, I'm not changing them like I did on this one where I'm like really making them compatible. I'm actually going to approximate them to be compatible. They're not compatible, but they are approximately 100. Are you with me? They're approximately 100. So at this point, we've got 900, 100, and then we've got this leftover 25 at the end, which is a standalone fine number. If you wanted to round it to 30, it would be okay too. It's not a big deal. But 25 is a perfectly fine number to leave it at. So we end up having 900, 125. What would that be as a total? 1,025. Now, it's worth noting that sometimes there's more than one pairing that could sort of be considered as compatible numbers, and my approximation and your approximation might not be the same, and that's okay. But there should still be justification behind it, right? So if you looked at this and you told me that 32 and 25 were compatible numbers, and that they were almost 100 or something, right? You know, we'd probably have to agree to disagree on that. That's not true, right? Like, it just isn't. So there are definitely some things that are wrong. I mean, like, I get that. But there's often other alternatives that are right, too. So, yeah, Rylan.
Is compatible only considered, like, if it's 100 or 1,000? Could that be
Yeah.
50?
So it could be 50, if you didn't have another option to try to make something into it. Like, so if you looked at this one and you were like, hey, 32 and 25 are approximately 50, and you went with that, it'd be okay. The problem is that then you still have the 62 to deal with on this one, which is not very nice either. So it doesn't help you very much. But usually you're looking for things that add to tens or hundreds to be compatible. Yeah. All right, so this next one is called grouping to nice numbers. Nice numbers means we're trying to get them to be compatible. All right, so we're looking for things that are nearly compatible. So looking at these options, there might be an arrangement that I make that's different than somebody else makes. Okay, this is a really good example of that. So we'll do it once, one way, and then we'll see if anybody else thought of different compatible numbers. So before any of us makes a statement out loud, I'd like for you personally to look at it and decide what you see as nearly compatible numbers and just draw some arrows, kind of like I did over here where I grouped them together, or over here where I was, that's not an example. Was it earlier? Here where I was kind of pointing at the arrows of what I was going to group together. So just group them together in a way that you feel like is reasonable as nearly compatible numbers, or what we would call nice numbers. Okay, so somebody tell me a pairing that you made. 35 and 71. Okay, so those are nearly what? 100, right? It's really close to 100 right there. Any others?
42 and 55.
Okay, so 42 and 55 might be one option. Did anybody else pick something different?
42 and 64?
Yeah, you could also pick 42 and 64. They're both pretty close to 100, aren't they? One's a little bit of an overestimate, one's a little bit of an underestimate. So I'll go with the one that I heard first, but you could do either one and it'd be okay. You're going to get slightly different answers, but your work justifies what you've done and it's all right. So we've got approximately 100 here, approximately 100 here, and you might choose at the end to just call this 60. You could leave it as 64 if you want. It doesn't really matter. But approximately, we're looking at 260 here, if you did those groupings. If you grouped the 42 and the 64, you might decide that the 55 is close enough to say it's about 50. So this is about 250, something like that.
To 60 and
Sure,
55?
you could, yeah. So it's an estimation, right? So there's kind of a ballpark of error that we would expect to have happen to what the answer is. What is not appropriate is to take your calculator and just figure out 42 plus 35 plus 55 plus 71 plus 64 and then round at the end. That's not compatible numbers. That's not estimation. That's not estimation at all. The point of estimation is to make the calculation easier, not to just make it less accurate at the end. If you found the exact answer, why would you want to make it less accurate? That doesn't make any sense. Okay? So the goal is to make the calculation easier. All right, so clustering is another one that's a really good example where it doesn't work all the time. So clustering only matters when all the values are pretty close to the same value to begin with. So if you take a look at 442, 538, 457, 554, and 497, what are they all approximately? They're all about 500, right? Yeah. So these are all approximately 500. Oops, not 5,000. They're all approximately 500. So what that means when we have that happen is that we're going to take that 500 times how many numbers we have. And we have 5 here. So what's 500 times 5?
2,500.
Yeah, those are approximate. Sorry, 2,500 is correct. Yeah. So this sum is approximately 2,500. Is that all right? Okay. You're very familiar with rounding. Your book leaves a little bit of wiggle room with rounding. Sometimes they'll just say round. And when they do that, like I'm going to pretend like that's what this one says essentially, it means you get to pick what place to round to. So it doesn't make sense to round equally to any of the places because you could just say round to the nearest whole number and then you wouldn't be rounding at all, right? They're all in whole number form, like that's not helpful. But you might choose, for example, to round to the nearest 1,000. Or maybe you choose the hundreds place. Those would both be sort of reasonable roundings that we could do at these particular values. Hundreds is going to be a little bit more work just because you're going to have 2-digit numbers at the beginning still because everything is in the thousands. But it wouldn't be as bad as, say, 4-digit numbers, which is what we have right now. So if we're doing thousands place, what we're doing is we're rounding to this value and we look at the number after it. If the number is 0 through 4, this number, 4,789, rounds down to 4,000. So the number at the beginning stays the same and everything else zeroes out. So it's the everything else that zeros. Or if we round up, it's because we've got a digit in the hundreds place in this case that's 5 through 9. So this one's in that case. So we take the 4,789 and we round it up to 5,000. So what's actually happening here, because sometimes people get confused with which numbers you're looking at and stuff like that, is that this number is between 4,000 and 5,000. Right? It is. 4,700 is between 4,000 and 5,000. So whatever we're rounding it to, it has to be either 4,000 or 5,000 if we're rounding it to the thousands. And the real issue is whether 789 is making it closer to being rounded up or to being rounded down. So on this one, 4,789, if I rounded it, I would get 5,000. Okay. We can do the same thing here. This number is clearly between 3,000 and 4,000. We're looking at the 1. The 1 means I'm going to round how? Down to the 3,000. So 5,000 plus 3,000 would be 8,000. So this is one approximation. If we wanted to do the same thing in the hundreds place, or if you were told to do the hundreds place, which you could be as well, it means that you're going to have these last 2 digits zero out, and they'll either be going down or going up. I would go 4,800, or I'd go 4,700. Right, so it's going to be between those because the first 2 digits, the 4 stays the same, and the 7 either stays as 7 or it goes to an 8. So this 8 right here is telling me what happens. Do I round up or do I round down? I round up. So this is 4,800 if I'm rounding to the hundreds place. And then over here, I either need to round down or up from 31. So I'm either going to stay 31 or I'm to go up to 32. What will I be doing here based on the number 4? I'll be going down. 48 is closer, making it closer to 3,100. So I'll be rounding down. This is 7,900. It's close to the 8,000 from the other one. So you're not having to do multiple problems. You just need to pick if you're given the choice. Or you need to do the one that's being asked if they tell you which one to do. Okay. I wanted to show you this idea of sort of the boundaries that are happening here, right, between 48 and 47, between 4 and 5, because what we're actually doing when we do this is called the range. So what the range does is the range takes each of our values and it rounds them down and it rounds them up. So if I rounded 370 down, I'd get 300. If I rounded 370 up, I'd get 400. And I do the same thing with 640. 647 rather, down would be 600, 647 up would be 700. I mean, those are the two different options. Round them both down, round them both up. And then we add what we've got as a result. So 300 plus 600 would be 900. 400 plus 700 would be 1100. And so what we would say is that our range is 900 to 1100. So range doesn't give us an exact value, it gives us sort of these boundary endpoints of where the value would be. The value is going to be somewhere in between 900 and 1100. Any questions on those? All right.